Okay, in this lecture, we're going to cover section 5.3, and this is probably going to be one of the most important sections we cover in this course for a few reasons. One, um, it's gonna tools that we learn in this section 5.3, and that's going to be on the fundamental theorem of calculus, if I didn't already say that, um, is that one way it's going to be important is that it's going to help us to simplify calculations of integrals considerably. Um, so we're going to have a lot of different tools available to us now to solve to solve and to compute integrals, rather than to have to resort to the complicated uh, limit definition we learned in the last section, which is the goal of mathematics, is to like make these ideas precise and rigorous, and then try to move away from those ideas by developing tools and techniques and methods for solving a wide range of problems. So this is a section is going to be important in that respect, and in another respect, it's going to be important is that it's going to tie together integration and differentiation. So it's going to have this will be a theoretical consequence of this section, and then there'll be some practical consequences. Um, so it's going to tie together the two most important areas of this branch of mathematics, that is differentiation and integration. Let me share my screen now. Hopefully you can see what I'm seeing. I'm going to open the book up now. So this is 5.3 on the fundamental theorem of calculus. So I'm just going to show you the two theorems. There's two parts actually, and really the second part's going to be the more important part. You're going to use the first part to prove the second part. Although they are both important, but I would say that the first part of the fundamental theorem of calculus is like a stepping stone. So here's the first part, and we'll go through all of this that I'm skipping right now, but I just want to get to the statement. Oops. It says the following. It says that if you have a continuous function, let's see, my pen, is it working? Yes. Sorry. It states that if you have a continuous function on a closed interval, then you can you can associate this other function g of g, also defined on the same interval, and it's defined as follows. It's defined as this integral. Then this function will also be continuous, and not only that, it will be differentiable no matter what f is. So f itself could be non-differentiable. So for example, it could be the absolute value function, which is not differentiable at the origin, or it could actually be the what's called the Weierstrass function, which is continuous but and differentiable nowhere. Doesn't matter, as long as it's continuous, you can define g of x, and this function will also be continuous and differentiable, despite whether or not itself is differentiable. And not only that, when you differentiate g, you get f back. So what this says is that g is an antiderivative of f. So in other words, the theorem says that every continuous function has an antiderivative. That's a nice result. So you can always associate an antiderivative to a continuous function. But how does this function work? How does this function well, let me get to that, the nitty-gritty details. So that's the first part, and then we'll go over it in more details, in more detail. But now let's go to the second part. So what is the second part? And here's a proof. We'll go through the proof. It's not terrible, but I think it's important to go through the proof. So here's the second part, which I think is the more important part. It states the following. It says that if you have a continuous function on a closed interval, then the definite integral, which you can in most cases interpret as an area. So this thing right here is just going to be this difference right here. It's going to be capital F of B minus capital F of A. So it's like evaluate the function at the endpoints and take their difference. What's f though? It's going to be any antiderivative of f. So that is, it's a function such that when you differentiate it, you get f back. So this is a nice result. So in other words, if you can guess what an antiderivative is, which we've done before, it's not terribly difficult. It's a little it takes a little getting used to because it's kind of working backwards from what we've been doing, but it's doable. You can guess an antiderivative, and once you've done that, computing the derivative is computing the integral is extremely easy at this point. So this is a very nice theorem that allows us to simplify computations. So let's go back to this, the first part to prove this. So as I said, this states that if any continuous function has an antiderivative, and another way of phrasing this part right here is to say, you can rephrase this as follows. It says that the derivative of this integral from a to x, notice the upper bound is a variable. It's not the integral from a to b, it's a to x. So x is your variable, it's changing. It can be some number from a to b of ft dt. When you differentiate this, you get f of x. So what this states is that in a sense, the derivative and the integral are inverse operations of each other. They undo each other. So this is why I was saying that it ties together these two operations that you learn in calculus. These two operations on which all of calculus is based, the derivative and the integral. So they undo each other in this sense right here. All right, so what does this function mean though? Maybe geometrically. Maybe how do you actually deal with this function? Well, as I said, the upper bound on the integral x is a variable. So we're not taking the integral from a to x, a to b. We're taking the integral from a to x. Of course, so now x is this variable that can vary between a and b. Of course, you can evaluate this function at b. So if you evaluate it at b, you get the integral from a to b. So now you're finding the integral over the entire interval of this function. And this will be a specific number associated to b. But more generally, you can have x be any number between a and b. And so the idea is you fix an x, then you look at the interval, you look at the sub-interval from a to x, and suppose your function's positive for a moment. So now the integral corresponds to the area. It actually is the area. And what you're doing in this case is that you're finding the area under the curve from a all the way up to x. Not all the way up to b, but like part of the way. So here, let me show you this picture to kind of illustrate this function. So hopefully you can see this. So here we go. We have in blue, the blue curve is our function. And the red curve is this integral we defined. This is actually not correct. You see, I don't know why it stopped. It didn't replay. But anyways, hopefully you can see where my cursor is. This x should not be an x, and this x should not be an x. This should be t and dt, because you want it to be different than the upper bound right here. You want these to be t's here. So just mentally in your mind, replace this x, that in the f of x with t, and this dx, replace it with dt. So let me refresh the page so you can see what's going on. So the blue curve is our given function. It's going to be some continuous function. And then g of x is going to be this integral that we defined in the first part of the fundamental theorem of calculus. And basically, this blue dot here, you can think of it as a bead, and you can see from the image, it's actually literally sliding along the curve. So this can represent a specific x value. So in other words, you're integrating up to the bead. And then the red curve is tracking how much area you're computing as the bead slides along. So you can see that the curve increases quite a bit because we're uncovering a lot of the area under the curve. But then once you get to the peak up here, you are starting to uncover less and less and less. You're still uncovering area under the whole curve from like 1 to 2, whatever the upper bound is. But then it starts to taper out, and that's why the curve is flattening, is getting flatter. So it starts to increase. We get a lot of area uncovered. We're still uncovering area, but now it's not being uncovered that much. It's starting to taper out. So this is what the way to think about this function. It's like you take a specific x in your interval from a to b. In this case, a is 0, and then b is, I guess, maybe 2 or something like that. And then you take a specific x between a and b, and you slide the bead along to that point. It will like trace out a certain part of the area, and that's the same thing as computing the integral of the curve, the function to that point. And then maybe you slide a little bit more, you get a specific x value, you plug it into your function g of x, and that will give you the area under that curve, under that of the area of the curve up to that x value. So that's one way to like visualize this function, I guess. So let me see. I think they show a specific example right here. So here's example 1. We have this function f, and the graph is shown. Yeah, so here's the function that we were talking about, and the you fix a specific x, and you can think like there's like a bead right here. That's the blue dot in the picture, and it's like you slide it along, and you're like uncovering some area under this curve up to this point x, and that's what this integral represents. That's exactly what this integral represents, that area, assuming the function's positive, which is not that big of a deal. And then, so in this example, we're going to assume we have this function f, and the graph is shown here of f. And then we're going to define g of x in this way right here. It's going to be 0 up to x. I guess I guess this is 5. So we're considering x between 0 and 5. And let's see, we want to calculate these values here. So if you plug in 0, that is, you plug in your left endpoint, you're integrating from 0 to 0, so it should be 0, right? That makes sense. There's no area. Now 1, when you compute 1, so we're taking x to be 1, we're going to be looking at this area right here, which is a rectangle, right? Or sorry, not a rectangle, a triangle. So it's going to be 1/2 base times height. So the height is 2, the base is 1, 1/2 gives you 1. And now if you want to compute g of 2, well, now g of 2, you take this, so like our bead is right here. Now we want to slide the bead along all the way to 2. So now we're not only considering this area, but now we're considering this area as well. That's what g of x is. Sorry, that's what g of x is right here. And in particular, g of 2 represents g of 2 is the area under all the way up to under the curve up to x equals 2, which, as I said, will be this triangle plus this rectangle. So we can take this integral, we can use our properties of integration to split the integral into 2 pieces. So in other words, you have 1 is between 0 and 2, so you can split the integral up from 0 to 1 plus the integral from 1 to 2. This one we computed already. This was 1. And this area right here represents the area of the rectangle. So it's just going to be the base times the height. So the base is 1, the height is 2. So 1 times 2 is 2, plus 1 is 3. So that's g of 2 is going to be equal to 3, because 3 is the area, this total area right here. And then you can just keep going on from there. I'm not going to do the rest of these because then now it gets a little tricky. So if you want to go to 3, 3 includes this area. So you can see this is like an increasing function. It's like you're accumulating this area. So when you go up to 3, so now the bead slides down to here. So now you include the area of this triangle, this rectangle, and then this kind of unusual shape here. This is not a nice geometric object, so we can't get an exact area, so they're going to approximate it. So yeah, you can approximate it, but I'm not going to care about it. So I guess it works out to be approximately 4.3. So 3 is from the rectangle. The number 3 comes from the triangle plus the rectangle, and then the 1.3 comes from approximating that area. And then you can keep going to 4. Now this is where it gets a little interesting because now we're talking about signed area. So this area right here is going to be negative. So now you're decreasing the area, right? So the curve is like going down, right? The when you if you plot g of x, I don't know if they plot g of x. This is just like what area you trace out at specific x values, but it doesn't look like they plot. Oh yeah, here's the plot of g of x. So when you get to so a specific when you plug in 2, you can like go up to here and it's like 3. So 3 represents so when you plug in 2 to this function right here, the height of the function above the x-axis is 3, and that's because that's the area under the curve up to the point 2. It's let me get rid of some of this. It's this area plus this area. So you could plot this function, and a specific height of this function will represent the area. And then when you get to 3, now you go through the x-axis and you're no longer adding area, you're subtracting area because this is going to be a negative number and as well as this. And that's why the curve at 3, it maxes out and it starts to go down because you're decreasing the area. And eventually, I mean, I don't know, depending on, oh no, he does go back up. So maybe it kind of goes up and so the area will start increasing again. But we're not really concerned about the function past 5. So that's how this function works. That's how you kind of conceptualize it, visualize it, and how you can compute it. All right, so now let's just go through the proof. So what are we trying to prove now? Let me get rid of this. This is kind of messy here. So let's go back to the statement and prove it. All right, so we have f is continuous on this interval, and then we're going to find g of x by this formula. And the claim is that this is continuous and it's differentiable. Now remember, differentiable implies continuous, so really all we need to prove is that it's differentiable. And not only that, but the derivative is of g of x is just the original function you start with. So really the heart of the claim, what we're trying to prove is that this is differentiable and the derivative is given as follows. So we need to compute a derivative. All right, so let's see what they do here. So we want to compute this difference quotient, right? Because that's exactly what we need to pick a limit of to show that the limit exists and therefore it's differentiable. So what we want to do is we want to take h such that x and x plus h are in this interval a comma b. All right, so now so h is going to be sufficiently small so that x and x plus h are all still in this interval a comma b. So we're going to assume x is in this interval and then h is small enough so that x plus h is here. All right, so now what is g of x plus h minus g of x? Well, by definition, let me write it right here so you remember what g of x is. It's going to be the integral from a to x of ft integral of ft dt. So when you take g of x plus h, you're going to take this x right here and replace it by x plus h. So that's why we're taking the integral from a up to x plus h. My computer's freezing for a bit. Hopefully it responds soon. All right. So that's why we get this first thing here, and then we're subtracting off the original function itself. So we're just subtracting this off right here. Oops. All right, so now um between between all right, so this is actually kind of annoying what they're doing here. We're gonna actually assume that x is positive, or h is positive. And the reason why is that because if h is positive, then x x is going to be between a and x plus h. All right, so x is between a and x plus h. So we can use one of those properties of integrals where you can split off the integral at that point, at this point x. So you can chop up the integral. So now what we have is we can split this piece right here into these two pieces right here. So we can split it as the integral from a to x plus the integral from x to x plus h. All right. So now what happens is that this first integral right here cancels with this one, and all we're left with is this. So this is what we're left with. So g of x plus h minus g of x simplifies to this. And then, of course, now you divide by both sides by h, and you get this right here. Now they say for now, let's assume x is positive, but actually you need to assume that kind of from the beginning, I guess. Otherwise, you can't do this step right here, or it would at least get messy, very messy. So we're going to assume that h is positive. That's not a big deal. When h is negative, you kind of just can tinker with the steps a little bit. All right, so here is going to be an interesting application of the extreme value theorem. Remember, the extreme value theorem says that if you have a continuous function, which we do, so we have a continuous function on this closed interval, then you attain your minimum and your maximum. So that is to say that there exists u and v in the interval such that f of u equals m and f of v is equal to capital M. And these are going to be your absolute minimum and maximum values respectively on this interval right here. They don't really say this, but note that u and v depend on h, because we're fixing a positive h. So if maybe h were smaller, and so this interval would be smaller, you might have a different maximum and minimum on that interval. It's possible that you could have a different maximum and minimum. So your numbers that you choose, u and v, could be different, and then actually m and m, lowercase m and capital M, could be different. So we just want to note that these two numbers, u and v, that you get, that which correspond to your minimum and maximum, they depend upon h. If you change h, you might get a different number. So that's okay. That's gonna actually, we're gonna need that fact. Which is, so I want to just point that out. These numbers depend upon the choice of h. All right, so now what we can say then is that because they're kind of being sneaky here, let me see if I can do this on the side. So what we have then is that so f of u and f of v are the minimum and max respectively on the interval x to x plus h. So that implies, what that means then is that f of u is less than or equal to f of t, which is less than or equal to f of v. And that's for all t in the interval. This interval right here. So this is the minimum value, this is the maximum, so that means every value of the function is somewhere between those two, because these are the minimum and maximum. But remember, there was this property A, it was about estimating integrals. So if you have this estimation right here, I don't know, maybe I can go back to it. Let me go back. So it's in the previous section, I believe. Right here. If you have your function is bound between two numbers. So in other words, if you have like a minimum or maximum, then you can basically integrate both sides of this inequality and you'll get the, yeah, you can integrate the inequality to get this. So we're going to use this property right here. So let me write this over here. So we have our inequality right here. And I'm going to integrate both sides. So integrate over x to x plus h of f of u dt, and that's going to be less than or equal to the integral of x to x plus h of f of t less than or dt, sorry, don't forget the dt, less than or equal to integral of x to x plus h of f of v dt. All right, now f of u and f of v are constants, so actually I can actually just take them out of the integral. So it's to be integral from x to x plus h dt less than or equal to the integral of x to x plus h f of t dt. And this is going to be less than or equal to f of v times the integral from x to x plus h dt. Now, when you integrate this right here, so you're integrating one function, the constant one. So what it will end up being is just the length of the interval. So you have f of u times the length of the interval, which will be x plus h minus x less than or equal to this integral right here, which is going to be related to our derivative, actually. And then this will be f of v times the length of the interval, which would be x plus h minus x. And then when you simplify everything, it'll be f of u times h less than or equal to the integral of x to x plus h of f of t dt less than or equal to f of v times h. Okay. And that's exactly what we have right here. So that's how they got that. They kind of just threw in a bunch of steps and didn't show them. So that's why we have these lines right here. All right, so now you have h here and h here. And what we're going to do, so we're assuming it's positive, so and it's not zero, of course, we can divide the whole inequality by h without reversing any of the signs. So this leads to this. But this thing right here in the middle is exactly our difference quotient with g. That was the first thing we calculated up here. Remember? Right there. All right, so now we have this. And as they say, this inequality, so this holds for all sufficiently small positive h. Well, you can do the same thing. You can go through all the exact same steps. You got to just do some slight modifications and prove that this inequality actually holds when h is small negative number. So that's important. We want it to be, because we're going to take a limit eventually, and we want it to be, we want this inequality to hold for x positive and negative, small though. Because we want to take the limit as h goes to 0, and when we take limits, you need to consider left and right hand limits. You're kind of implicitly computing those as well. Now, here's the important thing. What happened? So now we want to let h go to 0 because we want to compute this derivative. That's what we want to do. We want to compute the derivative of g. Now, because these numbers, remember, they depend on h. So when h goes to 0, these numbers really, to show that they depend, you should actually say u sub h and v sub h. So there's like, it's showing you that these numbers that you get from applying the extreme value theorem, they depend on h. But the important thing is that u of h and v of h lie in the interval from x to x plus h. They lie between these numbers. And when you let h go to 0, this number right here gets closer and closer to x, but these two numbers have to be between them. So in other words, they're getting trapped. It's like h is shrinking. It's getting smaller and smaller. It's gonna eventually go to zero. And that's like trapping. It's basically the squeeze term in a sense. Like you're squeezing, you have this interval. Suppose x is positive and our h is positive. So you're looking at this interval right here. And these numbers right here have to lie in this interval. But as h is getting smaller, this right endpoint is approaching this endpoint. So it's like any number is getting squished down to x, right? So what we can say then, um, so what's happening then is that as h goes to zero, u of h approaches x and v of h approaches x. They're getting squished towards x. And now by continuity, because f is a continuous function, when you take this limit as h goes to zero of f of u, again, it should be a u sub h, but whatever, that doesn't matter. It's the same thing as taking the limit as of f of u as u approaches x, but by continuity, that's the same thing as just plugging x in, right? All right. So now, um, so that's like basically one application of the squeeze theorem, but then we can apply the squeeze theorem again to this inequality. So we'll take the limit as h goes to zero of both sides. So I don't know if I have any room anywhere. Oh, okay. So what we're doing right here is, so this inequality implies that f of u sub h is less than or equal to g of x plus h minus g of x over x is less than or equal to f of v sub h. And then now you're going to take a limit as h goes to zero of f of u less than or equal to the limit as h goes to zero of this difference quotient, which we're trying to compute because we want to show that this is differentiable. So not only are we showing that this is differentiable g of x, we're actually also, by the squeeze theorem, determining that limit. So this is a really nice theorem because it uses every single idea that we've built up. It uses the extreme value theorem, it uses mean value theorems, it uses squeeze theorems. The squeeze theorem, so it uses a lot of different results, and it would make sense because it's a very deep result in calculus that you would need to use all the tools and machinery that we've built. All right, so now we know basically by this part right here, and these steps, that this limit right here actually just equals f of x, because as h goes to zero, u of h approaches x, and f is continuous, so it's the same thing as plugging x in. So now what we have when we take this limit, and now this is by definition the derivative. So what we have is we have that f of x, this thing right here is equal to f of x is less than or equal to g prime of x is less than or equal to, well, this is also f of x by the same exact reasoning. As h goes to zero, v sub h goes to x, and f is a continuous function, so just plug x in. All right, so now what we have is that g prime of x is less than or equal to f of x. Sorry, it's greater than or equal to f of x, but it's also less than or equal to f of x. And so the only way that can happen is that g of prime of x just equals f of x. And that proves the fundamental first part of the fundamental theorem of calculus. That proves that g prime of x is not only differentiable, but the derivative is this. So that's the conclusion. And then, as I said, you can rewrite the conclusion. You can rewrite this step right here in this way as well. If you want to just like eliminate g, this is what the fundamental theorem of calculus says using this Leibniz notation for derivatives. So it says that these are, in a sense, inverse operations of each other. All right, so let's look at some specific examples where we apply the fundamental theorem of calculus. So we want to compute this derivative. So notice that our f of t, if we define it to be this function square root of 1 plus t squared, this is continuous. So when we want to take the derivative, you just simply take the function you're integrating and replace t by x. Very simple. So a very easy application. Sorry. All right, what about this one? This one is not so easy. So let me open up Paint. This is example 4. This one's a little trickier. So let's work through this step by step. So we're in 5.3, I think. This is 5.3. This is on the fundamental theorem of calculus. And this is example 4. All right, so example 4 says we want to find the derivative of integral from 1 to x to the 4th of secant t dt. Now, you might say to yourself, "Ooh, this is really going to be really awful because I have the secant function." That's actually not the hard part. This shouldn't be the hard part for you. The hard part, not necessarily hard part, but the part that makes this different than the last example we looked at is that we're not integrating up to x, we're integrating up to x to the 4th. So if we want to differentiate this, we need chain rule. Because we're composing this integral with the x to the 4th function. So let me see if I can write this out as a composition explicitly. So let's let f of x, all right, let's actually let g of x, let's try to first, let's write this as a composition. Because I claim that in order to compute this derivative, you actually need the chain rule. It might not be obvious at first. You might just think, oh, well, this should just be secant of like x to the 4th. And if you said that, you'd be, this is wrong. This is not right. This right here. Because we're not integrating. Remember what the chain rule said. I mean, the fundamental theorem of calculus says. It's the function is defined as the integral from a up to x, not a up to x to the 4th, not a up to the square root of x, not a up to whatever. It's a up to x. So we need to use the chain rule if we're going to differentiate this. So to see how we're going to use the chain rule, let's first try to write this as a composition. So let's do that. So we're gonna, whoops. What we're gonna do is we want to identify our inside function. So let's say inside piece, the inner piece or the inner inside function. It's gonna be g of x, and I claim that it's gonna be the integral from 1 to x, whoops, of secant of t dt. And then I claim that the outside piece, the outer piece, outside function is going to be the 4th function. So it's going to be of x is equal to x to the 4th. All right, let's verify this. Let's compute this composition and see if we actually get function. And maybe I didn't do this right, actually, now that I'm thinking about it. So, yeah, I can see now that this is wrong. Sorry, I did not rehearse this example. I can see that this is not right. So let me get rid of this. I'm pretty certain it's not right. I think I got to switch these. Let me switch them. So let me delete this. All right. So I think you got to switch these actually. So let's say our oops. Inner piece, inner function is going to be still going to use g of x, but it's going to be x to the 4th. Yeah, I think this is right. And then our outer piece, outer function, is going to be the actual integral from 1 to x of secant x, t dt. All right, let's compute the composition to verify that we have the right functions. So by definition, this is going to be f of g of x. And then g of x is going to be x to the 4th. And now in order to evaluate f of x to the 4th, I need to go to the formula for f of x. And wherever I see an x, replace it by x to the 4th. So that's the only x in the formula, so I got to replace that by x to the 4th. All right, so this is the right composition. All right, so now we apply the chain rule. So this function that we're trying to differentiate is indeed a composition of functions. There's probably other ways you can write this as a composition, but this is the most straightforward way to do that. All right, so now by chain rule, the derivative of that integral, which we know is the same as this composition. So the derivative of this composition, and remember, it's the derivative of the outside function evaluated at the inside function times the derivative of the inside function. So maybe I should actually have written my derivatives up here. So let's go up here and compute these derivatives. So the derivative of g is going to be g prime, which is 4x to the third. And then the g of f, so it's going to be f prime. Well, to get this derivative, it's just going to be fundamental theorem of calculus. So this we get by fundamental theorem of calculus is just, ordinary power rule. So f prime of x is going to be secant of x. All right, so now what we have is f prime is secant of x. Well, let's plug some of these things in. So g of x is x to the fourth, and then g prime is going to be 4x to the third. And now this is going to be f prime, remember, is secant x. So it's going to be secant x to the fourth times 4x to the third. So it's be 4x to the third secant x to the fourth. So the secant part wasn't the tricky part of this computation, because the differentiating that integral function, it's kind of easy. It's just, you just peel off the integral sign and replace t by x. The hard part was realizing that this is not a straightforward application of the fundamental theorem of calculus. You actually also need the chain rule. All right, so now let's look at the second part of the fundamental theorem of calculus. And we'll prove that. This one is going to be easier. It's a little bit easier to prove. So as we noted in section 5.2, we computed some integrals using the definition as a limit of those Riemann sums. And this procedure was in general very long and very difficult, if not impossible. So this fundamental theorem of calculus is the second part is going to be extremely powerful. It's going to make these computations a lot easier. They'll still be tricky. They're still going to be tricky. And we're going to learn some more tools. In the next section, I think it's the next section, we're going to learn use substitution. That's going to be a nice, powerful tool as well. But this is going to be greatly simplify these computations. We won't have to take these limits anymore. All right, so let's remind ourselves of the second part of the fundamental theorem of calculus. It says that if you have a continuous function on this interval, and if you have an antiderivative, capital F, then to compute this integral over the entire interval a comma b, you just evaluate the antiderivative at the endpoints and take the difference. That's it. That's all you do. This is not rendering properly. I feel like it's going to freeze any second. Anyways, so here's how the proof goes. So define g of x to be this. We know that g prime is the derivative of, sorry, when you differentiate g, it's going to give you f. So that's to say that g is an antiderivative, right? This is the first part of fundamental theorem calculus. This is the one that required most of the work. Now let's take f to be any other antiderivative of f on this interval. We know lots of them exist. In fact, we know exactly what they look like. Remember, there's that corollary that said, if you have, well, this is not the right corollary. Remember what there was a result that said if you have an antiderivative, if you have a single antiderivative, then you have every antiderivative because they all differ by a constant. All the antiderivatives differ by constant. So what that means is that if you take a general antiderivative, capital F of x, it's going to be this specific antiderivative defined here plus some constant. All right, I'm not going to worry about these details right here. This is kind of just unnecessary. So now, just skip this part. Um, so what, um, so now if you plug in x is equal to a into the formula for g of x, this is what you get. So you're taking g of a is going to be the integral from a to a of the function, and that's just going to be 0 because you're not talking about any area, essentially. That's what that means. All right, so now here's the last line of the proof. It's pretty simple. So what we want to show is that what's the conclusion, remember? The conclusion is that if you want to compute this integral of f of x from a to b, it's just the difference, this difference right here. So let's compute this difference right here and see if we get this right here. So what we have is that f of a minus f of b is g of b plus c, because that's what f of x is. It's g of x plus c. So it's g of a plus g of b plus c, and then minus g of a plus c. Now these constants right here cancel, and all you're left with is g of a minus g of b. But remember, g of a is 0. So all you're left with is g of b. And so you just got to plug in b into the definition of g. So when you evaluate g of x at b, it's the integral from a to b. It's going to be your integral over the whole interval of this function right here. And that proves the result. So pretty straightforward. It uses a couple intermediate results, and of course it relies heavily on the first part, the fundamental theorem of calculus, but a pretty straightforward proof. Uh, so it might not seem like this is a nice result, but this is going to be a super nice result. So let's look at some examples to see why this is a nice result. In fact, actually, let me show you the example and we'll go through the calculation. Well, actually, I just show you this calculation here because it's almost like a one-line proof. So remember this integral we encountered in the last section, right? This was really difficult to calculate using the definition of an integral. And let's go back and remind ourselves how difficult that was. So, where is it? Let's see. Not that one. Let's see, where is it? I thought it was in 5.2. Maybe it was, oh wait, maybe it was in 5.1 actually. Uh, oh, here it is. So here we go. This is this integral right here. And we to set up this integral, we need to say, well, this is our function. These are our endpoints. This is going to be the width of the subintervals. So we're going to take the interval from 1 to 3 and divide it into n intervals of equal width. So they have to be of this width right here. And then these will be the right endpoints of the intervals, the subintervals. This will be the ith, x sub I will be the ith right endpoint of the ith subinterval. So it's described by this. And then, so now this integral will be by definition this limit, which is this, which is this. And then you had to ask a computer algebra system to rewrite this horrible sum right here as this. And then so now the integral could be written as this limit right here, because you replace this sum by this thing right here. And then you had to ask the computer algebra system again to compute this limit, and it will end up being this. So now I imagine you could probably figure out these sums and limits by hand, but I'm sure that they are absolutely positively awful to go through. So let's see how there's a lot of work here, and there's a lot of work being covered up because we're asking a computer to do a lot of work. So there's tons and mountains of work to just compute this one integral. Okay, let's see how easy it is now that we have the fundamental theorem of calculus. So as awful as it might have been to prove the fundamental theorem of calculus, the fact that this example is going to be done in one line is justification for proving that, because it's going to simplify the results a lot. So it's going to be it'll behoove us in a sense to want to prove these results. So let's go back to this example here. All right. So how do we calculate this without using the fundamental theorem of calculus? Well, you start with your function. You notice it's continuous everywhere. So and in fact we know it's antiderivative. It's because it's its own derivative. So the integral is just f of 3 minus f of 1. So it's e to the 3 minus e to the 1. And that's it. You're done. Of course, it says you can use any antiderivative of f. So you could take like e to the 7 or e to the x plus c. But notice this constant and this constant are going to cancel out in the computation because you're taking a difference. So the constants are going to cancel out. So there's no point in using these antiderivatives. Just use the simplest antiderivative you can. And so you use this one. So one line. Once you know that this, I mean, we already know these facts. Like, so this part of the proof is like unnecessary. We know that this is continuous everywhere, and we know it's antiderivative. The derivative of e to the x is e to the x, so it is its own antiderivative. And so there's the one line. So huge simplification once you know the second fundamental theorem of calculus, the second part. All right, let's see. Here's another simplification. We saw this problem. Um, we did this problem finding the area under the parabola from 0 to 1. That is computing this integral right here. And that was not terrible, but it was still kind of annoying and tedious. But again, this is a pretty, once you know the fundamental theorem of calculus, this is a very straightforward problem. It's basically, again, one line. So you have this function f of x. This is the function we're trying to integrate. It's the function whose area we're trying to find from 0 to 1. And you just note that this is the antiderivative. And you can just do that in your head. If you take the derivative of this, you will in fact get x squared. And then, so now this integral will just be, you evaluate the antiderivative at 1. So you have 1 cubed over 3 minus 0 cubed over 3. So it's going to be 1/3. And that's exactly what we found when we went through that example, I think in the first section. And it was, again, it wasn't terrible, but it was a lot more work than this. All right, here's another example. Let's see, we have one, see, I think we just have this one example we'll work through together. So we want to evaluate this integral, and this is going to be super hard if you try to do this by definition, but once you know the fundamental theorem of calculus, this will be a lot easier. So we have this function. It's definitely 1 over x. This function is continuous on the interval from 3 to 6. And the antiderivative is given by this. So if you differentiate this, you will in fact get 1 over x. But x is positive, so we can actually just drop, we're considering x in this interval, so it's positive, so we can actually drop the absolute value. And so our antiderivative simplifies in this way. And then, so now the integral, again, this is a one-line problem. This, once you know the fundamental theorem, it's just one line. All of this stuff is kind of just, we already know, because we talked about continuous functions. There was a whole section on antiderivatives and computing antiderivatives. So really the heart of the problem is right here, in this one line. So if you want to integrate 1 over x on 3 to 6, it's the same thing as evaluating your antiderivative at 3 and 6 and then taking the difference. And of course, you can use the property of logs. So you have a difference of logs. It's going to be the log of the quotient. So the logarithm of 6 over 3, and that will just simplify the log of 2. All right. I'm not going to go through 8. I encourage you to go through 8. I think there's an example or two we skipped. Go through those on your own. Go through this example. This will show you where it seems like the fundamental theorem of calculus breaks down, but it actually doesn't. So this is a good example to go through to figure out, to know, to have an understanding of what the fundamental theorem of calculus actually states. All right, so now here's just a more succinct way of writing. Well, this is just combining both parts of the fundamental theorem of calculus into one statement. So what it says is that you have a function g f that's sorry that lowercase f is continuous on this interval. Then this right here, define if you define the g of x in this way, then its derivative is given by this. So that means in particular that g is differentiable and continuous, and the derivative is just the original function itself. And if the second part says if you want to compute this integral right here, you just find any antiderivative and then just evaluate the antiderivative at the endpoints of the integral, and then take the difference. And of course, as we noted, part one can be written in this way to show you that these differentiation and integration really are inverse operations of each other. All right, that's all we have for now.